This is exam 2. So in problem number 1, we wanted to find the derivative of the cube root of x. And the first thing you need to do is to write the cube root of x as x to the 1/3 power. So the derivative of that will simply be 1/3 times x to the 1/3 minus 1, which turns out to be minus 2/3. And that's good enough. And number 2, you want the derivative of 8 to the x plus x to the 8th. And you have to realize that 8 to the x is an exponential function, so the derivative of 8 to the x is going to be 8 to the x back again, almost. The problem is 8 is not e, and so you have to multiply by that fudge factor, the constant, which you should remember and just memorize it. It's the natural log of the base, so natural log of 8 is the answer for the first term. Derivative of the sum is the sum of the derivatives, so you just take the derivative of the second part, which is 8 times x to the 8 minus 1, or 7. That's it for number 2. Number 3, you want the derivative of x to the 4th e to the x. And if you didn't realize that that's a product, you're done for. It's a product, so you have to use the product rule. So it's the first times the derivative of the second. You got to know the derivative of e to the x is e to the x. Plus the second, e to the x, times the derivative of the first, which is 4x cubed. Now this is a test. There's no reason for factoring this out. You're not going anywhere with it, so just leave it. That's perfectly okay. Number 4, you want the derivative of x squared minus 1 over x squared plus 1. There isn't any useful simplification, nor the numerator can be factored, but the denominator can't, so there's no canceling that you can do. So you're just going to have to bite the bullet and write out the quotient rule. So it's the denominator times the derivative of the numerator, which is 2x, minus the numerator, x squared minus 1. And notice I put it in parentheses here, otherwise I'm going to forget to subtract both of those things. Numerator times the derivative of the denominator, 2x, and all of that is divided by the denominator squared. Now here, as I've said many times, when you use the quotient rule, at least 9 times out of 10, this is going to simplify, and you can see stuff happening. You can either factor the 2x or multiply it all out. If you don't want to take your chances with factoring, then go ahead and multiply. You're going to get 2x cubed plus 2x, and now remember that minus has to be distributed, so you're going to have 2x times x squared, which is minus 2x cubed, and then you're going to have minus minus, which makes it plus 2x, and all of that is divided by x squared plus 1 squared. So that can be obviously simplified a little bit further, because stuff cancels, and the 2x cubed cancels with the minus 2x cubed, and 2x is 4x, so your final answer should be 4x over x squared plus 1 quantity squared. And that's number 4. For number 5, a few trig functions that you had to have memorized in terms of the derivatives. So for the derivative of secant plus tangent plus cotangent, the derivative of a sum is the sum of the derivatives, so we just take each one separately, cotangent x. So the derivative of secant is the secant of whatever times the tangent of whatever. Then the derivative of the tangent is secant squared of whatever, x in this case. And the derivative of cotangent is minus cosecant squared. And that's good enough. I mean, there isn't anything that's going to cancel off completely. Sure, you could probably find a common denominator, but not worth it on a test. Okay, number 6, the equation of a tangent line. So you're going to need the slope of the tangent line, and you need a point. I only gave you x equals 1, so you need to figure out what y is, and y you can get by plugging 1 into the function 2x squared minus 2x plus 3. So if you plug that in, you get 2 minus 2 plus 3, which is 3. So the point that you have is 1, 3. Now you need the slope, so you need the derivative, y prime, which is just going to be 4x minus 2 but that's the derivative at every point. You're not interested in the derivative at every point, you're just interested in the derivative when x equals 1. So you plug 1 in, so the derivative at x equal to 1 would be 4 minus 2, or 2. So now you know the slope, you know the point, so you can just write the equation. Y minus 3 equals the slope times x minus the x value. And that's it for number 6. Number 7 threw a lot of people, and I was very surprised because we had problems just like this on the quiz and on the exercises. So it's a simple chain rule problem. All you're told is that g is f of e to the 5x. So they didn't tell you what f was, but they told you that f prime at 1 is equal to 3, and g prime at 0 is equal to, I'm sorry, find g prime of 0. So that's the problem. Find g prime of 0. But they didn't tell us exactly what g prime of x was, but this is the best we've got. So we can calculate g prime of x straight from the chain rule. Chain rule says because this is a function of another function, we can take the derivative of the outer function, plug in exactly what's there, don't change anything, but then you've got to multiply by the derivative of what's inside. We've taken the derivative of e to the 5x many times. It's e to the 5x back again, and one more chain rule gives us a factor of 5 from the derivative of what's inside there, the derivative of 5x. So that's the derivative of g at x. The problem says find the derivative of g at 0, so you just plug in 0. So g prime at 0 would be f prime at e to the 0 times e to the 0 times 5. And now you can just read this off. F prime of e to the 0, e to the 0 is 1, so f prime of 1 is 3, times e to the 0 is 1, times 5, and that's 15. And that's it for number 7. Number 8, you have to calculate the derivative of the sine to the 5th of 1 minus 3x squared. Now the first thing you need to know is that the sine to the 5th means the sine of whatever, all of that to the 5th power. That's what you're dealing with. And so what you have is a power rule, just the high school rule. Anything to the 5th power, the derivative is going to be 5 times that anything raised to the 4th power, but then the chain rule says you got to multiply by the derivative of what's inside. Okay, the derivative of what's inside. Well, we got a sine, so we got to take the derivative of sine, which is cosine of whatever is there, 1 minus 3x squared. And then, of course, the chain rule comes along and says you got to multiply by the derivative of what's inside that, and that's just going to give us a minus 6x. So that's about it. We could rewrite it one last time, but that's not even worth doing. It's just, but I'll do it anyway. The 5 and the minus 6 consolidate to minus 30. You've got an x here, and then all that's left is this sine, which is to the 5th power, 4th power, sine to the 4th of 1 minus 3x squared, and then multiplied by the cosine of 1 minus 3x squared. And that's it for number 8. Okay. Number 9, we want an equation for the tangent line, but this time we're not given the function exactly. We're given an equation that gives us implicitly a relationship between x and y. So the equation is x plus y to the 5th equals x minus y. And we're given that it's at the point -1, 0. So we're going to need the slope. We've got a point, so that's not going to be a problem. But we need the slope. So we need dy dx, or we need y prime, which means we have to think of this equation as giving us y as a function of x. So we can take the derivative of both sides. Now here is one of the things that causes math professors to pull their hair out. I've said this also a million times. The difference between this and this. The first is the derivative with respect to x of. So it's a prepositional phrase without an object. The derivative with respect to x of. So you need to fill in the object here before you know what you're talking about. This is the derivative of y with respect to x. That's a complete noun, a complete phrase. The derivative of y with respect to x. What you want to do in this problem is take the derivative of both sides with respect to x. So what you want to do is take the derivative with respect to x of that and say that that would be the same as the derivative with respect to x of that. Notice the difference between doing this and doing dy dx, x plus y to the fifth. This means that you've got dy dx already calculated and you're going to multiply that by x plus y to the fifth. That's not at all what you're doing. You are taking the derivative of this thing. So that's what you have to write. So when you take the derivative of anything to the fifth power, you're going to get 5 times x plus y to the fourth. And then the chain rule comes along and says you got to multiply by the derivative of what's inside. And here, this problem was loaded with pet peeves for me. You have to multiply by the derivative of what's inside, and what the derivative of what's inside is going to be a sum. Now, a lot of people here just wrote 5x plus y to the fourth, and then they wrote this big dot, like times, and then they wrote 1 plus dy dx, which is right, sort of. I mean, it is the derivative of x plus y. It's 1 plus dy dx. But you see, the problem is this big dot does not tell you that this 5x plus y to the fourth has to be multiplied by that whole expression. The 5 times x plus y to the fourth has to be multiplied by the derivative of this whole thing, which is 1 plus dy dx. But it's multiplied by that whole thing. So that whole thing has to be in parentheses. The big dot doesn't do it. And sure enough, almost everybody who did this in the next step did not realize that this dy dx over here also has to be multiplied by 5x plus y to the fourth, which makes the problem a lot easier. Okay, on the right, the derivative of x minus y is 1 minus dy dx. Okay, now let me box this up so we can see it. There's a lot of junk on the screen. Okay, at this point, I could solve for dy dx. I'd have to distribute this all out. But that's not the question. The question is, what's the slope at this point? So since I've already taken the derivative, I can now plug in the x and the y. So wherever I see x, I can replace it by -1. Wherever I see y, I can replace it by 0. So this is going to be 5 times -1 plus 0, which is -1, to the fourth, times 1 plus dy dx equals 1 minus dy dx, which isn't so bad. And of course, -1 to the fourth is 1, so this is just going to be 5. And we can distribute that 5, so we get 5 plus 5 dy dx equals 1 minus dy dx. Get all your dy dx's on the left, and that's going to give you 6 of them, 6 dy dx. And on the right, you're going to get 1 minus 5, which is -4. So dy dx is -4 over 6, or -2 over 3. So that is the slope. And now you know the slope. You know the point is -1, 0. So the equation is going to be y minus 0 equals -2/3 times x minus -1, or x plus 1. Good enough. Okay, number 10. We want the derivative of the square root of the inverse tangent. Well, again, change the square root to something to the 1/2 power. So we've got the inverse tangent to the 1/2 power, and we want the derivative of that. What are we dealing with? We're dealing with something to the 1/2 power. So the power rule says the derivative of that's going to be 1/2 times whatever it is, don't change it, to the power 1/2 minus 1, or minus 1/2. But the chain rule then says you got to multiply by the derivative of what's inside. And that one you had to remember. Derivative of the inverse tangent is 1 over 1 plus x squared. And really that's about it. This is going to be 1 over the square root of the inverse tangent, and that's not going to help you at all, not going to simplify anything. This answer is perfectly fine. That's enough for problem 10. Number 11, you want the derivative of the log, 2 times the log base 10 of x. Well, I don't remember, so the first thing, because of this log base 10, I don't like log base 10 because I don't remember the derivative of that. It's going to have some stupid constant in front of it. So what I'm going to do is first say y equals log base 10 of x, and instantly change that into exponential form. 10 to the y equals x, and then hit both sides with the log that I do want, which is natural log. So natural log 10 to the y equals natural log of x, and so y natural log of 10 equals natural log of x, and so y, which is this guy right in here, is nothing more than natural log of x times 1 over log of 10. So here's another way to look at it. This is the derivative of 2 times, what did I say? This constant moves over to there, so it becomes 1 over natural log of 10 times natural log of x. So I'm taking the derivative of that mess, which looks horrible, but it's very simple because 2 is a constant, 1 over log 10 is a constant, so they just sit there while I take the derivative of log of x, which just is 1 over x, and we're done. Okay, that takes care of number 11. Number 12, we want to use logarithmic differentiation to find the derivative of x squared plus 1 to the sine x power. So the first step is to let y equal that, then take the log of both sides. So the natural log of y is the natural log of this. The reason we do that is to make the exponent come down. So we get sine of x times natural log of x squared plus 1. Naturally, natural log does not distribute over addition, so you're just stuck with that. But you can now take the derivative of both sides. The derivative of log of anything is 1 over that anything, but you're taking the derivative with respect to the independent variable x. So 1 over y is not the independent variable, so you're going to get the chain rule coming along. 1 over y times dy dx, or y prime, would be equal to. Now the derivative of this thing, you're going to have to use the product rule. So it's the first times the derivative of the second. Derivative log of anything is 1 over that anything, so I can just stick that down here. But then the chain rule says you got to multiply by the derivative of what's inside, so I get another factor of 2x in there. First times derivative of the second plus the second, log x squared plus 1, times the derivative of the first, which is just simply cosine of x. So that does it for the derivative of the right, and now all I need to do is figure out what dy dx is. So dy dx all by itself is y times all of this, and I remember what y is. So that's x squared plus 1 to the sine x power times that horrible mess, sine x times 2x over x squared plus 1 plus log x squared plus 1 cosine of x. Just a quick reality check. The derivative of any exponential function is going to be that exponential function back again times some other stuff. So that is what we're getting, so it works. Okay, we've got the helicopter problem. Helicopter is descending. I'm sorry, I said descending. I should have said going down. And it's going down at a constant rate of 2 feet per second, straight line, constantly 18 feet to one side of a pole that is 100 feet tall. So here's my pole that's on flat land, 100 feet tall. And that's a constant. It's not changing. All right, and let's see. There's a bright light at the top of the pole, so there's a light. And then there's a helicopter that's going down by the pole. So the helicopter is coming down here like this. So here's the helicopter at some point. And how fast is the shadow of the helicopter? Well, where's the shadow of the helicopter? Well, the light is casting the shadow by shining on the helicopter and blocking the light from here. So the shadow would be somewhere around here. This is where the shadow is. And the shadow is going to be moving this way, because as you come down here, you can see that the light is going to be blocking, the light is blocked by the helicopter, and the shadow will come this way. So the picture that I need is going to look like this. Here's where the shadow is located, and this is my height of the helicopter above the ground. So I can make that y. And then there's a lot of ways that you could set this up, but when I was doing it, I said, well, let's make the distance from the shadow to the pole equal to x. So here's how I think of it. X is this distance. All right, and since the pole is 18, or excuse me, the helicopter is 18 feet from the pole, and it's constantly 18 feet as it's coming down, so this interior segment right there is 18, and that would make this distance here x minus 18. All right, so there's my picture, and while I'm at it, well, let's see, what is it that we're trying to figure out? It says how fast is the shadow moving along the ground, so my problem is to find the change in this distance, dx dt, because that's what determines where the shadow is, the distance away from the pole, and the change in that distance is the speed of the shadow. The shadow's right here. So find dx dt when, at the moment, when the helicopter is 10 feet above the ground, which would mean y is equal to 10. Okay, so we've been here before. We need to relate the variables. So how about the ratio of x to 100? Oh, sorry, I left out something. They told us that the helicopter is going down at a rate of 2 feet per second constantly. So that means that y is changing. So dy dt, you can say, is 2, or negative 2 if you want to be technical, because it's decreasing. But 2 will be good enough. So the ratio of x to 100, because these are similar triangles, these two, this one and the bigger one, the ratio of the base to the height will be the same as the ratio of the base to the height in the smaller triangle. So if you multiply this out, you're going to get xy equals 100x minus 100 times 18, 1800. Okay, so we need to get derivatives into this problem somehow. So how about taking the derivative of both sides? We need the product rule, so it's the first times the derivative of the second, which would be dy dt, t is the independent variable, plus the second times the derivative of the first, dx dt. So that takes care of the left side. And the right side will be 100 times the derivative of x. And that's it. Okay, we can go ahead and start substituting what we know. When y equals 10, we can put y equal 10 in there. We know dy dt is 2, so we can put 2 in here. And we still need dx dt, but dx dt is what we're trying to solve for. So that stays, dx dt. Now I need to figure out what x is at the moment when y is 10. So when y is 10, what is x? And I bet I can get it from this relationship. When y is 10, let's just put 10 in here. Well, actually, we could put it in there. It might be easier without the fractions. So when y is 10, that would say 10x equals 100x minus 1800. All right, bring that 10x to the right. That gives us 90x equals 1800. So x equals what? 9 into, that's 20. X equals 20. So x is 20, so I can put 20 here. 20 times 2, the 2 was dy dt, plus 10 times dx dt equals 100 times dx dt, and dx dt is the unknown. So we'll bring everything with dx dt to the right. That gives us 90 dx dt equals, what is left over here is 40. So dx dt is equal to 4/9, or negative 4/9 if you're technical about that kind of stuff. Okay, number 14, as I mentioned in class, this was a surprise that people didn't get this. The linearization is just the equation of the tangent line written in L of x form. So the function is y equals ln of x. The point is x equals 1. You did need to know that when x equals 1, y is going to be 0. The log of 1 is 0. So the point is 1, 0. The slope is going to be y prime, which is 1 over x. Y prime, not at every point. At every point it's 1 over x, but at the point where x equals 1, that's going to be 1 over 1. So our slope is 1, and our point is 1, 0. So the equation is y minus 0 equals 1 times x minus 1, or y equals x minus 1. And the thing is, all you have to do is say this is L of x. L of x is the y, so L of x is x minus 1. So the linearization of the log is just the function x minus 1. Graphically, here's what that looks like. The log function looks like this. And the line x equals 1 is a line of slope 1, y-intercept negative 1. And it's going to come in like this. I'll draw it dotted. And then it's going to be tangent. I didn't draw it real well, but it's going to be tangent right there at 1, 0. So if you were to zoom in to this little portion of the curve, you would see a line of slope 1, and you would see a curve that are about the same. And that's the idea, that the curve is linearized or made straight in a small neighborhood, if you look in a small enough neighborhood. So this function does it. And then the last part of the question said, give us an approximation for a log of 1.1. Well, you just use the line instead of natural log. So natural log of 1.1 would be approximated by the linearization of x equals 1.1. So that's going to be 1.1 minus 1, which is 0.1. And you can check that out on a calculator. It's actually not too off, not too far off. Okay, number 15, the derivative of the hyperbolic cotangent. The only thing you had to remember here was, well, two things. Hyperbolic cotangent is cosh over sinh. So you should just do it with the quotient rule, which is the denominator, sinh, times the derivative of the numerator. Derivative of cosh, you did have to remember, is sinh. So we're going to get sinh squared, minus the numerator, cosh, times the derivative of the denominator, which is also cosh. So you're going to get cosh squared there. All of that divided by the denominator squared. And that's good enough. You might have remembered a formula that says cosh squared minus sinh squared equals 1. So this is the negative, this is actually negative 1 over sinh squared, which would be minus hyperbolic cosecant squared. But you did not have to do that. Okay, differential problem. You had to compute delta y and dy, where y equals x squared. So that you're given that delta x and dx are both 1, and the point that you're given is 1, 1. So the easiest thing to do is to calculate delta y. Delta y is just the change in y going 1 unit from 1, 1. So let's start the picture here. If you draw the graph of y equals x squared, and you draw the point 1, 1, and just take a step forward from 1 to a delta x or dx forward, that takes you to 2, then what's the change in y? Well, y goes from 1 to wherever this point is, which would be at 2, 4, because this is the graph of y equals x squared. So the change in y will just be 4 minus 1, or 3. So that's your delta y. And then dy by definition is the derivative, y prime, or dy dx, times, now that's a bad way to look at it, it's f prime of x times dx. And of course f prime of x is 2x, but it's not 2x at every point, it's 2x at this point. So it's 2x really at 1, so it's just going to be 2 dx. So this is dy. Oh, and we know what dx is, so this is just going to be 2. dx is 1. So dy is 2. So you can see that at this kind of granularity, where you've got a big step for dx and delta x, you shouldn't expect a whole lot. The linearization is going to be pretty lousy. And sure enough, if you follow the tangent line, let's use a different color here. Let's use that color. If you follow the tangent line this way, you're going to be underestimating the actual value. This is the value that you get by following the tangent line. So the approximation that you would get, well, let's see, dy is 2, and that is this distance from here to here. That would be dy. So that's the difference between, well, we just calculated dy is 2. So from here to here, you add 2 to 1, and you get 3. So this point would be 2, 3, as opposed to 2, 4. So your approximation for y squared, if you needed to do that using differentials with this kind of giant step, would be you'd be approximating the y value of 4 by the y value of 3, which is of course not real good. But obviously that is not a good use of the tangent line. You've stretched it way far beyond the curve. Okay, so we've just about shown everything here. We've got to show that the delta y is from here to here. Your dx and delta x are both down here, and dy is here. And that's really about it. All right, that leaves us with number 17, which is the, no, you're supposed to find a formula for dy dx, where y is the inverse cosh. And using the formula that cosh of cosh inverse of x equals x. So if this is y, then you could take cosh of both sides. So cosh of y would just be cosh of cosh inverse of x, which would be x. And then we've done this a bunch of times. We just take the derivative of both sides with respect to x. So the derivative with respect to x of this would have to be the derivative with respect to x of x. And obviously on the right, you're going to get 1. On the left, you have to have the derivative of cosh of y. Derivative of cosh anything is sinh of y, because that's what's there, though you can't see it anymore. It's the cosh of y that I have on the left side. So it's sinh of y, but the chain rule says you got to multiply by the derivative of what's inside y. So here's dy dx. And so I can solve for dy dx and get 1 over sinh of y, and finally just plug in for what y is. So you get 1 over sinh of y, which is cosh inverse of x. And that is good enough, even though there are identities that allow us to rewrite this in other form. This is good enough. Okay, I think that's about it for this test.